Okay, next up we would like to draw out some Lewis structures. So we start with H2CO3. As usual, count our valence electrons. We'll have 2 by 1 because of the hydrogen, plus 1 by 4, plus 3 by 6. And this is going to give us 24 electrons. To think about, we can label them H2, C, O3. And so now let's just draw out our skeleton structure. We already know carbon is the central atom because it can make the most bonds, 4. But we are actually going to place the carbon surrounded by oxygen and then the hydrogen. And that is just based on the fact that hydrogen can only make 1 bond, so that makes the most sense, so that it can make 1 bond here. And then let's start with 1 bond on each. And so this way, let's fill in the octets of each of them. And let's see if that adds up to our 24. And so we're going to have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So clearly here we have too many electrons, and so let's figure out where we can change the arrangement in order to make them 24. Now it's tempting to do it on any of the oxygens, but we're actually going to make use of the fact that we know how many bonds oxygen would like to optimally form to minimize its charge, and that's 2. We can see that this oxygen already has its 2, so it has a formal charge of 0 already, and so does this one. And so changing them won't benefit us because it's going to mess up the charge, and that would mean that it isn't the best structure that we can present. So the best oxygen to change is actually this top one to give it the 2 bonds that it would like to have, leaving it with a formal charge of 0 like the rest. And so let's see if we have our 24, 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So our valence electrons are all accounted for. Now let's check on our formal charge. On each of the oxygens, we'll have 6 minus 4 minus 4 over 2. And that's going to give us 6 minus 6, which is 0. On all of the hydrogens, we have 1 minus 0 minus 2 over 2. That's 1 minus 1, which is 0. And lastly, on the 1 carbon, we have 4 minus 0 minus 8 over 2, giving us 4 minus 4, which is 0. This is all expected. We had a net formal charge of 0. And so our valence electrons are all accounted for, and our charges are all accounted for. So this is the correct Lewis structure. Next, we're asked for any equivalent resonance structures. And so we need to think about what resonance structures mean. And so resonance structures are just a set of 2 or more Lewis structures that collectively describe the electron bonding of a single polyatomic species. By including bonds and fractional charges, they describe delocalized electrons in double bonds and lone pairs that a single Lewis formula cannot describe on its own. And so when we want more resonance structures, we need to figure out, can we move any of the electrons in double bonds or lone pair electrons to get another similar looking Lewis structure? In this case, no, we can't, because if we decide to move the electrons here, let's say to go back into a lone pair, we know that that would mess up the charges. Same thing here. If we decide to move these lone pairs on their own, it would mess up the charges and make them non-zero. And so this only has 1 equivalent resonance structure. For the following ones, that may not be the case. And so let's move on to our next one, which is Hco3 minus. Let's count our valence electrons. We're going to have 1 plus 1 by 4 plus 3 by 6 plus the additional 1 because of the charge. And that is going to give us 2 plus 4 plus 18, which just happens to be exactly what we have here. So we're still going to have 24 electrons to play with. Again, let's draw our skeleton. but remember we only have one H, so we can put that on either side. And so let's start by one bond on each and fill in our valence electrons and see if we have our 24. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So clearly, again, we have too many electrons. So let's see what we can do to bring the electrons down to 24. So we would optimally like to move 2 electrons into another additional bonding pair to do that. This oxygen has already made its optimal 2 bonds, which means we're going to be playing with one of these 2. And so let's play with the one on the top by getting rid of those 2 electrons and adding a bonding pair like that. And so this way we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So our valence electrons are now all taken care of this way. Next up, we need to check on our formal charges. We should be expecting a net formal charge of -1 because of this negative up here. So on the oxygens, we're going to have these 2 cases, which will label 1, in this case, which will label 2. So on the case 1s, we're going to have 6 minus 2, 4. So they both have 4 lone pairs, minus 2, 4, 2, 4. So they both have 4 electrons in bonding pairs. And that's going to give us 6 minus 6. So they will have a charge of 0. Let's check in on our hydrogen. We're going to have 1 minus 2 over 2, which is 1 minus 1, so 0, 2. On our carbon, we're going to have 4 minus 0 minus 8 over 2. 4 minus 4, going to give us 0. Let's check in on this second case, oxygen, where you have 6 valence electrons because it's oxygen. Minus, we have 6 lone pairs, minus 2 electrons in the bonding pair. So we're going to have 6 minus 7, and that's going to give us -1. These formal charges make sense because we expected a net formal charge of -1, which is what we do have. So the negative is going to be there. Okay, so this is going to be our Lewis structure, right? And now we want to figure out if there are any resonance structures for that. We can do that by seeing if we can move any lone pairs or bonding pairs, if it's a double bond, in a way that doesn't mess with the valence electrons and doesn't mess with the net formal charge. And indeed we can, if we decide to actually instead have this one having the 8 electrons and this one having the double bond instead. And that way we would move the charge from there to here, and this would have the charge of 0. And so now let's write them out as separate things. So we will have C with the double bond at the top, attached to the OH and attached to the O. And then the minus would be on this one. Or alternatively, we can have a double bond here instead and the minus on this one. So this one remains OH. And this one gains the double bond to have that, and the minus on this other one. We can't move the double bond to this because that would make this one negative, this one -2, and then this one will be positive. And so we'd like to minimize the charges on the individual atoms each time. In that case, yes, the net charge would be correct, but you wouldn't have minimized the charges on the individual atoms. And so we only have 2 equivalent structures. Okay, and then last up we have Hco3 Minus. Let's count our valence electrons. We're going to have 4 plus 3 by 6 plus 2, and that is again going to give us our 24 electrons to play with. And so now let's write out our structure. Okay, and then let's start with single bonds on each and filling in the octets of the oxygens. Okay, and then let's see if that all makes sense. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Let me just make sure I got that right. 6 by 3 plus 6 by 3. sorry, 2 by 3. 3 by 2 for the bonding electrons, and that's going to give us 18 plus 6, which will give us indeed 24 electrons as counted out. But, so yes, this is all correct so far. Let's check if this is the version that would minimize our formal charges on each. And so on each of the oxygens, we're going to have 6 minus 2 over 2. And so that is going to give us a -1 charge on all of them. So we could all have minus charges. And then let's check on the carbon. If we have carbon with a full octet, which should be optimized, and we'd have 26 electrons, which would break that, because the valence electrons would be too many. And if we have carbon just like that, then we're going to have 4 minus 0 minus 6 over 2, which would give us a +1 here. And so in this case, we have two charges that we can neutralize with each other. And so this is obviously not the best structure because you haven't minimized the individual formal charges. And so let's go about doing that by adding a double bond. And so now let's see what we have. We have this oxygen with a formal charge of 0, this carbon with a formal charge of 0, and your 2 minus charges. So that all makes sense. We had a 2 minus in the question, and we've achieved it, and the valence electrons all check out. And so now we want to see if we can come up with any resonance structures for this, and indeed we can by moving this double bond around. And so we'd have 3 structures. We'd have what we've drawn. Additionally, we could have this double bond here instead, and this one with the full octet. And so we'd have and so the 2 minus charges would be down here. And lastly, we have if the double bond was here instead. And so you'd have the 2 minus charges here. And so these would be all of our resonance structures with a total charge of -2. And that's going to be your final answer. So you have 3 equivalent structures. And those are your final answers.